Good afternoon. Guess what? We have a new name. If you aren't aware, we're now the Voyagers Conservancy. And this is the first time I get to introduce our webinar today using Voyagers Conservancy. If you didn't know about it, we just changed the name and we have a new logo. You can see it there at the bottom right of your screen. And even though we have a new name and a new logo, we're still the official nonprofit friends group of Voyagers National Park that supports the park in various ways, including applying for dark sky certification and bringing you free educational programs like our Night Sky Explorer series. If you'd like to get more involved with this conservancy, visit our website, get in touch with us to volunteer, to make a donation, or just contribute in any way. If you're a parent or a teacher or even a kid, you can look at our web pages and find distance learning activities as well. Few things to remind you that make sure that you turn off your video and keep your microphones muted. We will use the chat box to give you information, share links from AstroBob, and use the chat box to also ask your questions so that AstroBob will answer them at the end of the presentation. So now I'd like to introduce Voyager Conservancy's star volunteer. And AstroBob, he fell in love with stargazing as he was a kid. He has this passion that he shares with everyone. And he's been an amateur astronomer, photographer, and photo editor at the Duluth News Tribune before he retired. He's taught at UMD Planetarium for many years. He's written books about sky watching. His most recent is about science versus pseudoscience in astronomy. So please welcome AstroBob.
Thank you very much. Very much, Jackie. Really appreciate that. And welcome everyone. Glad that you're here to hear a little bit about the Northern Lights. And first I want to wish you all a great Thanksgiving week, however you celebrate it, in a small group or a little bit larger group, but not too big. And I hope you all stay safe. We can always look at the night sky. It's one of the many things have changed during COVID times here, but one thing that has remained the same is the night sky. You can always go out and look up. So we will talk about the Northern Lights today, but before we begin with the main part of the presentation, I want to alert you to an event coming up that you may want to watch. And with that, we're going to head over and I'll share my presentation screen with you. There's the Northern Lights. Oh, I wish we could have that right now tonight, but I've got cloudy skies here and I don't think there's any aurora in the forecast. But the event that's coming up, I may have mentioned this a few weeks back, but there's a penumbral eclipse of the moon, and that will occur on Monday morning, November the 30th. And a penumbral eclipse is different from a partial or a total eclipse of the moon because instead of the moon passing through this part of the Earth's shadow called the umbra, that's the part where inside the umbra, the Earth, the globe of the Earth, completely blocks the sun. Right, so in there you get a very dark shadow. It looks like a bite is taken out of the moon when it moves into the umbra. Instead, the moon will only pass through the outer part of the shadow, which is kind of a mix of shadow and sunlight. So the shadow is grayish. It's not a dark bite, but you can still see that penumbral shadow. Take a look at it here. This was a recent penumbral eclipse from February 10th, 2017. Here's the full moon rising up from Lake Superior over the Duluth Ship Canal. And I bet you can see where the shadow is. If you guessed on the left half of the moon, you are correct. See how hazy it is? Kind of faint, but yet it's there. That is the outer shadow of the Earth. And a similar eclipse, very similar as a matter of fact, will occur in November. It will be, although the event lasts several hours, it'll be most obvious when the moon is deepest in the Earth's shadow. And that's best between I know those hours look scary, believe me, 3:15 to 4 a.m. Whew, it's kind of harsh. But if you were to just pick one time to look, it would be right around 3:45. And then the moon will be deepest in shadow. And you can see it'll be off in the western sky to the right of the constellation Orion, not too far from the bright star Aldebaran in the constellation of Taurus. And you'll notice that the upper half, the right half of the moon will look a little dusky, kind of dark, and that's the shadow. Maybe the best way to see this eclipse is just to get up for even 10 minutes, take a peek out a window, that way you can stay warm, and then head back to bed. So I hope you do get to see it. If you have clear skies, go for it. Well, we're going to talk about the Northern Lights. And one fascinating thing about the Northern Lights is that it involves the largest body in our solar system, which is the sun, and also the very smallest things that we're aware of, which are atoms, and in particular pieces of atoms, the pieces and parts. You've probably heard of these before, but an atom basically is made of a nucleus, which has got a bunch of protons in it, and around the nucleus, there's a cloud of electrons. These are very tiny particles. So that's what an atom is, and the parts of an atom. Now, the sun, when you look at the sun, you see the sun shining. The sun is a very interesting type of material. It is not actually made of neutral atoms the way, say, my hands are or my shirt is. The sun is actually made of something called plasma. And plasma is the fourth state of matter. Just to refresh, let's look at those states of matter. Remember these? A solid, like an ice cube, right? Or a snowflake. That's one state of matter. The second state is a liquid where the atoms get to kind of roll around. They're not bound into a lattice. The third state is if you apply heat. By the way, if you apply heat throughout this process, you can turn an ice cube into a liquid and turn a liquid into a gas where the separate atoms or molecules are far apart. The fourth state of matter is if you keep heating that material up to an extremely high temperature, you'll actually separate the electrons from the atoms, from the nucleus of the atom. And then the material becomes ionized. In other words, it can conduct electricity, and it can also produce a magnetic field. And magnetic fields are really interesting and important when it comes to northern lights, as we'll learn in just a moment. So it actually gets so hot that you have the little electrons over here and the cores of the atom over here, and they're all mixed up in a soup together called plasma. And the sun is super hot. The surface is like 10,000 degrees, and the core is on the order of 30 million. So it's not made out of ordinary matter like we have here at our desks and computers. It's made out of plasma. Here's a closer look at plasma. Here's typical molecule or an atom where you have the nucleus and the electron going around the nucleus. And here is a plasma, positive nucleus separated from its little brothers, the electrons. That's what the sun is made out of. Oh my gosh, look at all of that. When you plug in a lamp and you turn it on, the lamp works because electrons are racing along that wire and they power the bulb. Interestingly, as those electrons move, if you have anything that's electric and it's moving, a current, it produces a magnetic field. So there's actually a magnetic field invisible to your eyes from that wire. Anytime you have moving electrons, moving ions in that plasma state, it produces a magnetic field. And the magnetic field is very much like the magnetic field you see around a bar magnet, where it has a north pole and a south pole. And in this picture, you can see that iron filings have been sprinkled around the magnet. So it reveals the otherwise invisible magnetic field. That's always there. You can't see it, but the particles of iron will outline it for you. Now, the sun being incredibly hot and being made of all of these electrons and protons flowing around one another, these charged particles, guess what happens? They're flowing and they're moving, so they create magnetic fields. Matter of fact, a whole lot of them turns the entire sun into literally a gigantic magnet with a north pole and a south pole. And here it even has a magnetic field sprouting from it, kind of like Einstein's hair, or maybe my hair, north and south. And if you've ever seen a total eclipse of the sun, you'll see that the moon, which is shown here right in the center of the picture, the moon covers the sun, and you'll see these beautiful forms around the sun called the corona. Notice anything there? Does it remind you of anything? Yes, a magnet. Check it out. All of the sun's atmosphere is also aligning, just like the iron filings along the sun's magnetic field. So it looks like a giant bar magnet, doesn't it? It's a fascinating thought. By the way, I do have a demonstration for you of plasma right here. If you're wondering, well, Bob, the sun is so far away, is there anything close that I could see that's made out of plasma? And yes, you could see a beer sign or a neon sign. Anytime you see a neon sign, the gas in there is a plasma. But I've got a demonstration right here. Let's see if we can show it to you. This is one of those little plasma balls you get for kids. You can use this for a little room light. Do you see that? An electric current goes through there, and it ionizes, it strips away the electrons from a gas called xenon inside that bulb. And that's what's creating those little squiggles and wiggles of plasma. There it is. You could touch it here and touch it there, do all kinds of fun things with it. So that's one way that you can see and experience some plasma right here in your own home. Fascinating thing about the sun. I mentioned it's like a giant magnet, right? Well, the sun spins. It turns on its axis the way the Earth spins on its axis. But because the sun is made out of this ball of electrified gases, these gases can sometimes concentrate to form powerful magnetic fields on the sun's surface where it really gets strong. And those places on the sun where the magnetic field becomes very, very powerful are called sunspots. Here you can see the sun rotating, and those dark spots are sunspots. If you had a magnet, it would suck it right into that sunspot because it also has a powerful magnetic field. It's very concentrated magnetic energy. That's what a sunspot is. Some sunspots are even just like magnets in that they have a north and a south pole. Look at these. You can see groups of spots, and one end of the sunspot group will be the North Pole, and the other end is the south. South, north. It's just like a magnet that pops up from beneath the surface of these hot gases and concentrates the magnetic energy and makes that spot. Well, sometimes sunspots aren't that simple. They're not just north, south, and well-behaved. Sometimes, and this is when things get exciting, north and south are clustered. It has lots of norths and souths right near each other in the same spot. And the sun, even though the pictures that you see here make the sun look smooth and placid, it's actually not so smooth and placid. The surface is bubbling. If you could get up close and look, it would be like staring into a boiling pot of soup, just like that. And this is kind of a simulation, but just to give you an idea. So you've got these sunspots, you got these north poles and south poles, the surface is boiling. Can you imagine what might happen from time to time? Yes, those magnetic norths and south, where all that energy is concentrated in the sunspot groups, those fields can twist, they can cross, they can snap. And when they do, they release powerful energy in what we call a solar flare. A typical flare is equal to several million of the largest atomic bomb or thermonuclear bombs that humans can make. Millions of them. And that's in a typical flare. So these are very powerful explosions that occur on the surface of our star. Here's a picture of one. This was taken in ultraviolet light, which is why the sun looks a little strange. But these flares release powerful ultraviolet light. They can release X-ray light, and they also blast out material from the sun, like you see here, into outer space. And that material is made out of, well, sun stuff, right? It's made out of nuclei of atoms and electrons, positive and negative. It's made out of plasma. And that big plasma cloud streams away from the sun, sometimes at many hundreds of miles per second. across space. And if the sunspot flare is positioned in such a way that it faces the Earth when the big event happens, it can be directed towards our planet. Now, the Earth, which you see off to the right here, also has its own magnetic field. And our magnetic field is like a shield, kind of like Orion the Hunter's shield. And that shield normally allows all the material from the sun to flow past it with no effects on the Earth. It really does protect us. But every so often, that material, especially if the magnetic field, the north-south in there, the magnetic field points to the south, it will hook in, it will go right into and hook up past our defenses into our magnetic field. Here you can see the sun's particles, and here's the Earth's field, like the bar magnet once again. And here it's found a way to sneak in and hook in to our magnetic field. And that's when the excitement starts, because those fields, they cause the particles to stream right on down at many hundreds of thousands of miles an hour. Straight down, they follow those field lines, just like the magnet, straight down. And those lines end when they hit the atmosphere. They go right into the upper atmosphere, typically about 60 to 100 miles overhead. And they slam with great power and speed into the atoms that are up there. And our atmosphere is made of mostly nitrogen and oxygen. And they knock the electrons right out of those atoms. And the electrons go back to the atoms because they want to return to their, what we call the rest state. They want to relax after being all energized by the particles slamming them. And when they relax, they release light. And the light color depends upon the atom. Nitrogen is often pink, and oxygen releases green light, which is very typical for the northern lights, as well as red, both green and red. So the atoms, the electrons bounce out, and then they fall back. And when they fall back, they release that energy. And those billions of atoms, with each one a shot of tiny energy, combine to produce the beautiful phenomenon of the northern lights. You get these fantastic rays. The rays really describe the paths of electrons spiraling down the field lines, like the field lines of that magnet that you saw with the iron filings. Now, this is a satellite view of the northern lights. And you can see the United States here, some cities, and look at this from outer space. What an extensive display of northern lights. Notice that this has a bit of an arc shape to it. Do you see that? Up here and down there. That arc is part of a circle, or an oval actually, called the auroral oval. And that auroral oval is centered over the Earth's north geomagnetic pole. All right, it's magnetic pole, not the physical North Pole itself, but the Earth's geomagnetic pole. And lucky for people who live in northern Minnesota, northern Michigan, that puts the aurora sort of close to us compared to people who live in, say, England. Even though they're at a higher latitude further north, the oval is kind of slanted over onto our side of the globe. So as a result, we tend to get the northern lights more often than, say, people in northern latitudes in Europe, like England, Ireland, and so on. So this is, again, part of that oval. Now, during a quiet time, when there's no big storms, there's no giant flares, the oval is always there, but it's kind of pale and small. All right, there's always some particles. They're always coming in. So you often get auroras here across central Canada almost every night of the year. But when we get a flare, lots more stuff comes flying towards the Earth, works its way down to the upper atmosphere, and the oval intensifies and it expands and it moves southward right over the top of the United States. So you can see here during this evening, when was this? This was the 1st of January in 2016. If you were living anywhere around here, you could see clearly a beautiful display of the northern lights in the northern sky. Here's an orbital view. Isn't that fantastic? This was taken from the International Space Station. So you can see Minneapolis down here and Fargo. And here's Duluth right where I'm sitting. And from space, you can look way out over the horizon and you can catch part of the auroral oval right there. I'm sure that night from Winnipeg and even Duluth, the people there would have seen some northern lights in the northern sky. So I mentioned flares. Flares are the main way that northern lights occur, especially when the sun's really active, like at the top of the solar cycle, when it has lots of sunspots. And by the way, that is going to occur in the year 2025. We have now passed the minimum of the solar cycle, and we're headed on the way back up. So things are only looking brighter as far as more and more and better northern lights displays. This is a kind of a view of the sun's corona. You can see it's just always streaming and flowing. Interesting thing about the corona, occasionally it develops holes. All right, and these holes are areas where particles can stream directly out into space from the sun. They're not buckled down as you see here in these little yellow areas. Those are powerful magnetic fields that sort of buckle down and trap the particles, prevent them from streaming away, unless of course there's a big flare. But these holes can develop in the corona that allow material to stream out all the time. And it comes at us again at several hundred miles per second. And if a hole is pointed our way and the cloud arrives with the proper orientation, it can link in to our magnetic field and give us northern lights. During the times of low solar activity, such as we are in now, coronal holes are responsible for many of the displays of northern lights that we see. Here's the cool thing about coronal holes. Sometimes they can last for months. All right, sunspots, they can last for weeks typically, usually not too much longer than a couple of weeks, but sometimes. But coronal holes, as the sun rotates, and the sun takes about 4 weeks for a rotation, coronal holes can come around again and again. And so if you have an aurora caused by one of these holes, you can anticipate sometimes seeing it again just a little less than a month later, and then perhaps even another month after that. That's exactly what happened last year. We had a coronal hole aurora on August 29th. It came back around on the 25th. We saw another one, and then it came back in October. So we had 3 months in a row when you could anticipate and you could see northern lights from this single feature that just persisted for so long. Now, here we're going to talk about just a slightly technical thing, but it's really easy to understand. Storms, they're called geomagnetic storms when we have these auroras. And sometimes they can be minor or moderate or extreme. A minor storm, you would see the aurora in the northern tier of the states, right along the tops, northernmost. During a moderate aurora, the oval expands further south so that people in Illinois, Ohio, Massachusetts, Colorado would see the aurora. And during a strong storm, you can see it even further south. And of course, I'm not going to read all of this, there's a lot to read, but there are various things that can happen during the northern lights that could impact power lines and oil pipelines and even satellites too. Because you got to remember, you've got electrons streaming into the Earth's atmosphere at high speed, and that's an electrical current. My gosh, and an electrical current, and it varies all the time, can cause electrical currents in things that are electric on the ground, like power lines. So it can have an effect on infrastructure and power lines. Anyway, each storm, minor, moderate, strong, severe, extreme, is associated with what we call a KP index or number. A minor storm is also called a KP5. Moderate, a KP6, strong is KP7, 8, 9, and so forth. So anything below KP of 5 is usually very faint from the northern United States and usually is not visible from the central US. But as you climb in the KP numbers, they become more broadly visible. These numbers, we get them from a system of what are called magnetometers that measure magnetic activity way up in the atmosphere. And there are 14 of these magnetometers around the globe, and they're on all the time. This is one of them. This is up in Canada. And they're on all the time, and they're measuring those magnetic changes. And those go into a forecast. And we'll talk about that in just a moment. I want to show you some examples what the aurora looks like depending upon what the KP number is. This is for the upper Midwest. When KP is 5, you will usually see a low glow down there. And if you can get a really good, clear view of the northern horizon, you'll notice that the glow looks like an arc. That arc is actually part of the auroral oval. That's what you're seeing. That's why it looks like kind of a rainbow, because you're seeing a slice of an oval. KP5. Sometimes during a KP5, you'll see a double arc or even a triple arc, but it's usually very low in the sky. When the KP reaches 6, sometimes that arc will break up and you'll see these beautiful rays that will form along the arc. And you get a little more color too. That's what's so fascinating. KP7 or 8, my gosh, if you see in a forecast that the KP is going to be 7 or 8, then you should drop what you're doing and head out right now and look for the northern lights, because that usually means that like the whole northern sky is filled up and there's lots of activity. We just had some northern lights. November 21st, this was taken, I didn't take this photo, but I hate to admit it, but I was sleeping at the time. This was probably sometime around 12:30, 1 o'clock in the morning. Occasionally I will sleep, but we did have northern lights that night. It was a KP4, actually it went to KP5, so it was a minor storm. And it's just recorded beautifully here. You can see the reflection, the beautiful green reflection in Boulder Lake, north of Duluth. It was taken by a good friend of mine named Clint Austin. So on the Voyager webpage, you're going to see several links today when you go back and check it out. One of those links will take you to the Aurora Forecast. It's called the 3-day forecast. And you can get a subscription if you want to this forecast, and it will be delivered automatically several times a day to your email box. Or you can just bookmark the site, go to it every day or whenever you feel like it, and see what the forecast is. And the thing to look for in the forecast is the KP number. Here it is. This is from back in October. KP index forecast, October 23rd through 25th. Here's a 4, there's a 5, 4, 4, 3. So you can see a little bit of aurora potential. A 5 means a minor storm, KP5. Then it drops back down for the next few hours. And then it really gets low down to 2 or 3. At 2 or 3, you won't see anything unless you live up in central or northern Canada. I want to point out also, when you do get the forecast, is to look at the time. The time is given in what's called UT, Universal Time, which is the same as Greenwich time, pretty much. So that's the time it is in England. So for you, if you live in the eastern United States, you've got to subtract 5 hours, 6 for Central, 7 for Mountain, 8 for Pacific. Again, if you see 5, that's a minor storm. 6, definitely worthwhile going out. 7 or higher, run. Again, this link will be on the site, and I encourage you to check it out. Just a couple more things I wanted to point out. You'll often see posted online beautiful aurora pictures. Matter of fact, sometimes they're so beautiful, they're unbelievable. And you might wonder, my gosh, when I go out, I don't see that. Why does it look so different to me? Well, the reason is a camera has the ability to record a time exposure. It can gather light over many, many seconds. Typically, when I take pictures of the aurora, I photograph for about 20 to 30 seconds. So it pulls in so much light that it reveals lots of structure, and it also shows lots of color. Those colors are real. It's just that sometimes they're quite faint, so we can't see them with our eye. Instead, what we see looks more like this: white, pale rays, and then down here, just a hint of green. That's typical for an aurora. However, not to say that some auroras aren't extremely colorful. Some are purple, there are deep greens, there are intense reds. So you can see all the colors, but in a modest display, it often looks colorless, at least the rays, and green down where you can see the bow. And that's again because our eyes work in real time. We can't gather in the light like the camera does. Another link that you're going to find on the website at Voyagers is a link for an Aurora forecasting app, both for Android and for iPhone. And they're both free. And I encourage you to go over there, download them. They have little alerts on them to let you know what's going on. So be sure to check that out as well. And with that, I'm going to come back at you. And if you have any questions, I'm free here to answer, or if something was unclear. And by the way, I do apologize if my internet connection was a little slow at times and my voice got stretchy. I hope it snapped back so that you could still understand what I said. So I'll wait to see if you have any questions.
Bob, could you show us your demonstration with the plasma bulb again? It didn't come through on the screen.
Oh, really? Well, probably because it was so small too, I would think, but maybe this will be better. Here we go. There we are. I take it that's probably a little clearer.
Yeah, I think that that you still had your screen sharing on, so it was behind it and we couldn't see it.
Oh,
If
yes.
you would just go through it again. I think that would help everyone.
Oh, okay.
Very well now.
We've got one of these little plasma balls. People often buy them just for like room lights or night lights or something. And the ball is filled with xenon gas, all right? And then there's an electric current that shoots electrons into that xenon gas at very high speed. That electron knocks electrons off the xenon gas, and it makes it ionized, just like the sun. So it's a plasma when you turn on the electricity. And what you see there are little jets of plasma, just like, it's, again, similar to what you find in a neon lamp or on the sun. And what's cool is that you can take your finger, hopefully, maybe you can see this, or maybe not, but you can take your finger and you touch the globe. And we're very conductive, the human body, so the electrons want to go right into us when we touch the globe. You don't feel any shock, by the way. It's perfectly comfortable. So I encourage you to get one of these. I got mine over at Menards for like $10. Couldn't believe they sold them, but it makes a wonderful demonstration. And some of you might like it as a nightlight.
Thanks, Bob. We have a couple questions coming in. First of all, what is the forecast for next week and are there any good nights?
Aurora forecasting is not a perfect science yet. And so that's why they give a 3-day forecast that's fairly accurate. Beyond 3 days, it's a little iffy. However, and I didn't include this link, there is a 27-day forecast too that you can check out. You can just type in 27-day forecast Aurora, and you could look out a full solar rotation about 27 days ahead to see what's up if there's aurora. Right now, I'm not aware of any possibility for northern lights in the next few nights. However, I would suspect that the aurora that we saw on the 21st of November, due to the coronal hole that I mentioned, that will potentially repeat, come the time of the winter solstice. The other thing about the northern lights is that when the moon is out and it's really bright, they can be hard to see. So sometimes you can have northern lights, but they're really not visible. So the best time to see them is if they happen at the same time the moon is around 1/2, like first quarter phase, 1/2 or less, or not in the sky at all, of course, that's the best.
All right, next question. Have tests ever been done on humans in the closer vicinity of strong storms?
To see what the effects are of them, I assume. The good thing about our atmosphere, even if particles, by the way, make it through. First of all, let me just answer the question. I don't know of any tests that have been done on people to see if there's any effects like that, except the most obvious one, the effect of wonder of looking up and seeing something crashing, these crashes of light in the sky. Oh, yeah, that is something. That definitely has a powerful effect. But as far as like physical effects or something, I'm not aware of any tests. Remember that even if those particles make it down the magnetic field, follow those lines, they are being absorbed by the atmosphere. They don't make it down to the surface. So our atmosphere and the magnetic field are what really protect us. They work together to protect us. And in the process, the atmosphere lights up and makes for a spectacular show. So we're safe to look at the northern lights any night, even under the greatest storms, even when it seems like something is going to come crashing down on you. Just take it all in.
Excellent. Okay. Are equinoxes better times to expect auroras?
Yes, that is true. They can occur any time of the year, but it's the orientation of the Earth with the sun's pardon me, the Earth's magnetic field in relation to the sun at the equinoxes that seems to favor a tighter or an easier connection with material streaming from the sun, allowing it to penetrate our defenses and make it down. So yes, equinoxes are one of the best times to be looking and anticipating northern lights. And by the way, I keep referring to them as northern lights. Probably should call it aurora, right? Because at the same time we see the northern lights in the northern hemisphere, of course, people in New Zealand and Antarctica view the southern lights, or what's called the aurora australis. So although they're not identical hemisphere to hemisphere, top and bottom, they're very close and they do happen at the same time.
Okay, if someone made a trip to the far north and happened to be there on a night that it's predicted very good northern lights, could they still be disappointed because they wouldn't see the colors with the naked eye? And is there a way to experience those colors other than through a camera lens?
Well, I can say that I've seen many, many displays of the northern lights, and I can tell you that if you're in a dark place and your eyes are adapted to the night sky, to the darkness, you will almost always see green. The arc is almost always green because it's usually among the brightest parts of the northern lights. I guarantee you that you'll see that color, but it's just more pale than normal. It depends upon the intensity of the display. The bigger the bigger and the brighter the display, and you're going to have those when you go much further north, like making a special trip to Alaska or up to northern or central Canada. The bigger the display, the more color you're going to see. You will see some deep, subtle reds and some faint pinks. But again, many modest displays don't show much color except for that beautiful greenish arc. And that arc, that green arc, that's from oxygen. I love to think of it as, wow, it's not only oxygen is produced by green plants, but it also happens to be the thing that is producing the green color of the northern lights.
Okay, it looks like we just have one more question, and I'm sure many people want to know the answer. Astro Bob. I can answer. The next Astro Bob will be on December 8th. And Bob, would you like to tell us what it'll be about?
Oh, sure. Yeah, it's an event I can pretty much guarantee. Like Northern Lights is still kind of iffy because we do our best to predict it, but has its own way of doing things sometimes, like nature does. What we will see though, in the next couple of weeks, and what I'm going to talk about is the Geminid meteor shower, which is the best meteor shower of the year, hands down. We would expect during the Geminis to see like 50 to 80 meteors per hour. The moon won't be in the sky. So I'm really looking forward to this, and I'll be talking about that meteor shower and also go into a little more detail about the great conjunction of Jupiter and Saturn that's going to occur on the winter solstice. So those two topics will be our next topic in 2 weeks.
All right, that was our last question. So just again, we'd like to thank everybody for watching. We have our new logo. We have the same web address here for voyagers.org/dark skies. And we've got the Astro Bob's blogs down here. So thank you, Bob, for tonight's webinar.
Thanks for having me.